Alright, we're going to proceed to do problem number 8 of homework number 7. Problem number 8 deals with the Poisson process, which we've done in previous homework exercises on other homeworks, but basically here it defines it as by the following properties in according to the stochastic process. The number n, which is going to be written in terms of the times t1 and t2, alright? So, in the interval between t1 and t2, such that the length is the difference between the two, and we define a Poisson random variable with parameter lambda t, and the actual probability of that n equals k is going to be the standard Poisson equation that we've learned to use, e to the negative lambda t times the quotient of lambda t all over the k all over the k factorial. Now, the problem also tells us that if the intervals t1, t2, and t3, t2, 4 are non-overlapping, then the random variable of n at t1, t2, and t3, t4 is independent. Finally, the final property it offers us is that at the time moment t, there is no more one Poisson point. So, these are the definitions we got. We form a stochastic process. We define that x of t as being equal to the n from the time points 0 to t. And what the equation is asking us, is going to ask us to do, is define the expected average of this x of t, as well as define the autocorrelation of this x of t at t1, t2. Those are the two parts of this equation. So we're going to proceed. Now, how do we figure out what e of this stochastic variable is? Well, we use a lot of the things that we know from before, how our probability is written by this equation, and how the summation from, we can see that basically this equation begins at 0, alright? Because like if k is equal to 0, 0, it's not defined in a negative value. That's where it starts and it goes to infinity. So that's how our equation is defined, right there, okay? And as we go through infinity, it all adds up to 1. Now, we could actually derive what the exact expected value of x is. We've done that in past exercise. The only difference here is that we're going to be doing x in terms of t. In the end, we just basically can tack on the t more or less, and that's what we end up doing. So we can actually break this down. We've done this in previous homeworks. But basically, if this is equal to 1, we can bring in the e to the negative lambda over to get this equation. And then if we take the derivative of both sides, this just ends up being e to the lambda again. We take the derivative of this according to lambda. This is going to be this is going to end up being k times lambda to the k minus 1, which we have right here. All right. The thing we can do is multiply both sides by lambda, which will get rid of this negative 1 on this side, bringing over the lambda onto this side. All right, so we got that equation going. And then if we bring over the e function to here, we end up getting the summation that equates to e to the negative x right here. All right, this is equal to that. And as you can see, the only thing left on this side is going to be the e to the x is going to be equal to lambda. So basically, if we're doing it in terms of t, the equation, we could, before I get to that, you could see how we could continue to do the derivation of this, like get e to the x squared and do this process all over again. In that case, we would get lambda over lambda Poisson. I wrote that in right now just for part B real quick, but we'll get back to that. Just for this question where we're actually asked what this is, what we end up with is basically that the expected value of the stochastic function is lambda times t. All right. Now, if we have to figure out the autocorrelation of this equation, well, we end at t1, t2. Basically, as we know, autocorrelation is basically the product of our stochastic function, at these two time points. We take that product, we do some arithmetic right here. I won't get into it, but basically we added and subtracted, made it a constant term. This ends up being 0. We break it down. this actually ends up equating to this right here. Alright? This e to the negative t1, this difference right here, which we know is going to be independent from what we were given up in our givens for the problem, and this t ex squared, which we actually got right there. I mean, when we actually take t into account, this ends up being lambda t times the sum of lambda t plus 1. So we actually have all the different parts. I mean, this we know to be lambda. This is going to be the expected. It's going to be lambda. We'll see here. Yeah, let me just show you. Here, it's better if I can get a problem like this. So, as you can see, lambda to the t to the first ends up being that first term. The second term, which is multiplied by, is going to be lambda t2 minus lambda t1. That corresponds, all right? And then the this term right here ends up equating to that term right there. So what we do is if we actually work out all the problems right here, we actually do the multiplication, terms actually cancel out, and we end up with lambda squared, the product of t1, t2, plus lambda times t1. And that's going to be in the case where t1 is less than t2. For t1 greater than t2, it's going to be the same derivation. The only difference is this added t1 at the end. It's going to be substituted by an added t2. So it basically, those are our two parameters to actually get it. Our final equation for the autocorrelation is going to be lambda times this product right here, lambda times t1 times t2, plus, depending on whether t1 is a smaller number or t2 is a smaller number, we're going to add on that number, so the minimum of t1, t2. And that's the end of problem number 8 for homework 7.